Brushing up on our basic knowledge, we know that red, green and blue colors combine together to produce a broad range of different colors. For example, a yellow color is given by 100% of contributions from red and green. On the other hand, a gray color requires equal contributions from all three colors. Similarly, a signal is made up of complex sinusoid. This is a very interesting concept, as we will see now, that even a square wave, which is a signal with an edge, can be thought of being composed from a set of sinusoids with different frequencies. In this example, we have just two sinusoids of different frequencies, 1 over t and 3 over t, and they add up. While this is not approximate, we can see where it is going. As we increase the number of frequencies in this signal makeup, we get closer and closer. So this figure basically captures the essence of this frequency domain decomposition of a signal. This is approximately a square wave. The lowest frequency is given by this time domain signal. The next frequency is given by this time domain signal, and so on. So when we add these together, we get a signal like. In this GNU Radio example, we explore the frequency domain, in which we discover a very interesting way to see how different time domain signals are actually constructed from a set of complex sinusoids. This was the claim of Fourier series and Fourier transform, and the flow graph I constructed here is a demonstration of that concept. As usual, the title I've chosen exploring frequency domain, and hence the corresponding ID. The generate option is Qt GUI. We have already encountered Qt GUI range block, and here I'm choosing a fundamental frequency f0, f or f0, and the default value is 1000, and the stop value is 2000. We will see what role this frequency plays. Checkboxes is something we have not encountered before. So the method to include is that we define an ID, and I'm choosing an integer value. So a default value is 0, true is 1, false is 0. So that I'm actually multiplying something with these values to turn them on and off. What exactly I'm turning on and off? The signal sources. 4 checkboxes, 1, 2, 3, 5, 7. 4 signal sources, 1, 3, 5, 7. Why 1, 3, 5, 7? This we will discover later. But what I want to show is that the sample rate is the sample rate, and then the waveform is a sine. The frequency is 1 times f0. Do you remember the f0 is a fundamental harmonic? As you would have guessed, the other next frequency would be 3 times f0, 5 times f0, 7 times f0. The amplitude is 1 times h1. So when I will turn the checkbox off, the amplitude would be 0, and this signal source would play no part in constructing the signals. When I turn the checkbox on, it will contribute its output to this addition block, and its output will be represented in the cumulative waveform. After the throttle block, I just display the waveform and the spectrum. Let us run this flow graph and see what it does. So here we are, and it is a little bit outside my window, but I try my best to include everything we want. Right now there is no harmonic which is selected. Or another way of doing this is to arrange these in a horizontal manner. That we will do as follows. So we use the GUI hint 0, 0, the position, 1 row, 1 column, the span. Then 0, 1, 0, 2, 0, 3. And let us see if we leave the rest, we can arrange yours. No, it does not arrange them properly. So we have to select these ones as well. And 1, 0, and this is a slider. I can give it 1, 2, 3, 4, a row span of 4. 2, 0, 4, 1. 3041. 30 is the third row, first column, 4 is the row span, 1 is the column span. And let us see if it is right. So the mistake I have done is that there is only one row and there are 4 columns. One row, 4 columns. One row, 4 columns. Now that looks better. Let's see. And that's how we bring everything into our window. So with these settings in place, let us see what happens if I turn the first harmonic on. So now we can see a nice sinusoidal real waveform and two spectral impulses. The frequency is 1 kilohertz, so 1 kilohertz and minus 1 kilohertz. The spectrum span is always from minus fs by 2 to fs by 2, in this case minus 32 by 2 to plus 32 over 2. And I can see that if I turn the fifth harmonic on, it will a higher frequency and 5 kilohertz, minus 5 kilohertz spectral impulses. And I can have this 7 kilohertz and so on. Now, let us start with the first harmonic. So when do this, and in addition, we also want to show the third harmonic. Can you see something? This waveform is resembling a familiar waveform, not exactly, but it's starting to look like a familiar waveform. Let us add one more harmonic and then one more. So we can see that this plus 7 kilohertz, minus 7 kilohertz impulses come due to this, plus minus 1 from this, and so on. So each time we turn them on and off, we remove the impulses. So if I do it in the reverse order, it might be, or in any random order, it might be easier to detect it. Plus minus 5 kilohertz, plus minus 7 kilohertz, plus minus 1 kilohertz, and plus minus 3 kilohertz. The point I'm making is that it is starting to resemble a square wave. So this is the actual claim of Fourier series and Fourier transform methods, that a time domain waveform, if it satisfies some given requirements, can be built by a combination of complex sinusoids. This is why these signals are so important in our DSP applications. I can also increase the frequency, and you can see that it's getting more and more resemblance. The spectrum is broadening due to the higher frequency. Having said that, I just want you to notice something here, is that for the first harmonic the amplitude was 1. For the second harmonic the amplitude was 0.33, 1 by 3. For the fifth harmonic 1 by 5. For the seventh harmonic 1 by 7. Why did I choose this? Because if you do the derivation for Fourier transform for square wave, then the spectral impulses at these frequencies 1000 f0, 3 f0, 5 f0, and 7 f0, 9 f0, they all have amplitudes 1 over the respective harmonic. This gives us an insight into the discrete Fourier transform as well, because the discrete Fourier transform is exactly about the amplitude contributed by different spectral impulses. Although I have shown you a continuous time and hence Fourier series application, the concepts from discrete Fourier transform, they can be taken directly from here. Before we explore what this flow graph is doing, I want you to go back to a previous exercise where we built a square waveform, an approximate square waveform, through a combination of sinusoids. So here we have a fundamental frequency 1 f0 with an amplitude of 1. A component with 3 f0 frequency and with an amplitude of 1 over 3. 5 f0 with an amplitude of 1 over 5, and 7 f0 with an amplitude of 1 by 7. So we saw the output where we selected different frequencies. So if it's just one single sinusoid, two spectral impulses in the frequency domain, and we added one more and one more, we see that it starts resembling a square wave. When I look at these waveforms, they look like Dilbert's hairstyle to me, and so on. So with this in place, focus on the new exercise. This is the exercise in which we take the reverse route. Let us see how. So we are testing the frequency domain, and everything else is you're already familiar with. The sample rate has been chosen as 32 kilohertz, and a slider has been defined with the cutoff frequency of a low pass filter. Although we will cover low pass filter in lecture 2 or like module 2 or chapter 2, since most people have a general idea of what filtering is and what low pass filtering implies. Basically, a filter which lets the lower frequencies pass and stops the higher frequencies. I have included here to show you a really interesting concept, and a variable with an FFT which defines the size of our FFT. I have disabled these blocks, which I will use later. You can do it with D or right click and select disable. Now here, as I said, we are taking the reverse route. So we start with the signal source, which is a square waveform. The frequency I have chosen is 1000 Hertz. An offset of minus zero point -0.5 just implies that there is no DC offset, because by default, the square waveform in GNU Radio Companion has a DC offset of 0.5. One thing you can do with the flow graphs is that you can read the documentation. On some blocks, the documentation is good. On some blocks, documentation is really simplistic. So where we can take advantage of where it is well written. So the square waveform, a throttle block to limit the CPU resources, and then we have a low pass filter. Let us see the options. It's an FIR type, which is finite impulse response filters, and float to float input, float output. Decimating and interpolating does not matter to us because we are not changing the sample rate. That's why I've chosen one. If I would have easily chosen interpolating, and this option should have been one, it doesn't matter because we are not changing the sample rate. Gain I have chosen as 1 for this example. Sample rate is a sample rate, the cutoff frequency, transition width 1000 hertz. The window is Blackman, and this beta is related to Kaiser window. And since we have chosen Blackman window, this doesn't basically matter to us, this option. Time sync, frequency sync. Let's see what this flow graph is doing. So here we have a square waveform and its spectral representation. Now you get a really general idea that a square waveform has been actually built up of plus minus 1 kilohertz, plus minus 3 kilohertz. But let's see this in a little more detail. So now what I do is that I enable these blocks which I disabled in the previous case. I go to the number of inputs, select as 2, and then I connect this output to the input. What is this? This is just um, a vector of with a single impulse. Now, a single impulse in frequency domain is a constant. Why did I do that as a source? Because I wanted to show the spectral representation of a low pass filter. We will just see that along with the spectral representation of the signal. Let us see what happens when I turn this on. And here you can see that the low pass filter, since the cutoff frequency is fs by 2, fs is 32 kilohertz, the frequency cutoff frequency is 16 kilohertz. This low pass filter actually passes all the frequencies. Now we will start reducing the cutoff frequency. And now you can see that some of the sinusoids which were represented by spectral impulses in this region have been filtered out, and the waveform is starting to look a little deteriorated. We keep reducing the cutoff frequency, and here you can see that up to plus minus 9 kilohertz is being passed. As soon as I reach this point, you can recall that the square waveform which we built in the previous flow graph was actually built up with individual sinusoids which were the harmonics of a fundamental frequency f naught. And when I reduce the cutoff frequency more, then more spectral contents are filtered out, and it starts to resemble a little bit of a combination of sinusoids. After removing the component plus minus 3 kilohertz, we are left with almost a single sinusoid with plus minus 1 kilohertz. And we remember we started with a square waveform, and this is what we are left with. So this is what the concept of a Fourier representation of a signal is, whether it's a discrete Fourier transform or a continuous Fourier transform, whether this is a discrete Fourier series or a continuous Fourier series. The concept is that any signal in time domain with some limitations can be represented by a combination of sinusoids in frequency domain. And that's what I wanted to show you, that a square waveform in this reverse route was built up of individual sinusoids. As an add-on, we can see the functionality of a low-pass filter. If I reduce the cutoff frequency further, it cuts off the spectral components which were plus minus 1 kilohertz, and we are almost getting to no signal.
In 1672, Newton demonstrated that the sunlight can be broken into 7 colors. A prism is a tool that tells us the intensity of each color. If we assume that they have equal contributions, then discrete Fourier transform exactly does the same job as a tool that decomposes a signal into its constituent complex sinusoids. And more importantly, it tells us the contribution from each complex sinusoid. We say that DFT finds amplitude and phase contributions for each of these and these are called analysis frequencies, where the frequencies are given by k over n, and these are the complex sinusoids, and we have a set of n discrete frequency samples. This is all the DFT does. The most important DFT pair we've encountered again and again in signal DSP is the rectangular signal versus a sync signal. So if we have a rectangular signal in time domain, it is given by a sync signal in frequency domain. I have plotted the magnitude here, but the important point here is that the width of the rectangular signal determines the zero crossings of the sync signal.
In the previous flow graph, we introduced frequency domain and saw the spectral representations of a cosine and a sine. Now what we do here is something really interesting. We take the one next step to see what the actual QT GUI frequency sync represents. Start with here, the title is DFT leakage and true spectrum, and the tab widget basically collects the time, FFT and spectrum. I will explain these what they mean under one tab. So the variable we have is NFFT, FFT, which is 32, and I have again imported pi. Remember that we can insert Python commands anywhere here. So I have imported the value of pi. The sample rate I have again chosen N32. We will see why. And again, we have decided to take a slider, to choose a slider which is signal frequency, and its value goes from minus MFT over to NFT. The difference, however, as compared to the previous flow graph is that there are no integer steps. Now we have, in fact, fractional steps. We will see the effect soon. Let us see what the flow graph is doing. The signal source is again a cosine floating point values, and The signal frequency defined by the variable signal freq. Float to complex for the FFT, and the signal is being shown by the time sync. This QFFT block is actually not a GNU radio block. I actually built it as a hierarchical block. I'll just show that to you. So here you will see that FFT block, stream to vector, vector to stream, and I have a paired source and a paired sink. The reason I've done is that if you see the space in this flow graph, you will see the QFFT range takes a very less amount of space as compared to I have chosen to put the stream to vector, FFT, and vector to stream. I have to pass it a parameter which is an FFT. These hierarchical blocks are made as follows. So you after that giving it an ID and a title, instead of choosing a Qt GUI generate option, we choose a hierarchical block. That's all. And the category I have chosen as Q blocks, which means that all the blocks I have made will be found under this heading. So let's go back to QFFT, where the FFT length is 32. We will see the effect. Let's run the flow graph. And here first we see that due to this tab widget, we have time, FFT, and spectrum. When we will click one, we will see that output. That we will do later. So the flow graph is running, but we are not seeing this waveform changing. Why? Because I have chosen the number of points on my time sync equal to 32, which is the same as the period, one full cycle. Now, let us go to the frequency domain and see, as we saw earlier, this is bin 0, bin 1, and bin -1. So a real cosine in frequency domain is 2 spectral impulses. Let us change the frequency to 2. Now we should see 2 full cycles. 1, 2. 2 full cycles in 32 samples. So the frequency, discrete frequency, is 2 by 32 cycles per sample. Its FFT, however, does contain impulses, but they are not 0, 1, 2, and -1, -2. They are at +2 and -2, but they are not simple spectral impulses with zero quadrature part. In fact, we have seen that the quadrature part has sprung up. Why? Because when you are changing the frequency from this slider, the phase was not synchronized. So now this waveform is not starting with a zero phase. If it was, so for example, if I close it and I choose the frequency as, sorry, that default frequency as 2, I will have two impulses at +2 and -2. And if I do choose it as 1, then again we will see that there is a Q part involved. The interesting thing is that the magnitude spectrum would still show us the two impulses. Time to move into decimal frequencies. So let us change the frequency to say 2.4. And the interesting thing you will notice here is that the flow graph, which was not moving, is now started moving in time domain. This is because for the integer frequencies, I had chosen for the time sync to show 32 samples only. And we had for integer number of cycles in those 32 samples whenever the chosen frequency was an integer. So you will see it will stop. It does. Again, if I choose it as a decimal frequency, it starts moving because there are no full periods in 32 samples for that frequency. Let us see the FFT now. Now comes the big part. You see, for the integer frequency, we had just the spectral impulses, and all the energy in the other 30 bins was 0. For a decimal frequency, this is not true, and the energy is being represented in all the other frequency bins as well. This is called DFT leakage, discrete Fourier transform leakage. Let us change the number of points in FFT now to 1024, which is the same as in the frequency sync, which we never saw before. Now the FFT size and the number of displayed points is the same. When we run this flow graph, so the first thing we see is that the time domain, they have lots of periods because we are just displaying more number of samples. And let us undo the stem plot option so that we can see a continuous spectrum. Here now we have two impulses at the signal frequency and there is no Q part. And now when we go to the spectrum, which is the display of this QT GUI frequency sync, we see that we have two impulses at plus minus 2 Hertz. The difference, however, is that here we are displaying it in the linear scale and here it's in the dB scale. That's number one. The other thing is that the spectrum which is displayed by the QT GUI frequency is actually the energy spectral density, which is magnitude of the FFT square. So if xk is the FFT, then this QT GUI frequency sync displays xk magnitude squared. So this is how we have these two impulses, and due to choosing a sample rate of 32 and a frequency of 2, which means that we have a perfect integer number of cycles, we don't have anything here. The window we chose was rectangular. And now we will change different settings. We'll see the importance of increasing the number of points. Let us change the signal frequency to a decimal number. I had to choose the same option for the Q plot as well. Let us change the frequency. To be consistent, I'm choosing 2.7. You can change it to any other frequency. And this is how we see the DFT leakage. Before I go back to the integer frequency, so that when the side lobes rise, we can see them. So let us see what happens. And here you see that the side lobes are, now we don't have any two simple impulses like before, and we have lots of energy in these side lobes. This is due to DFT leakage, and this is how most of the actual plots you will see will look like. Now if we want to see the effect of the rising side lobes, so we choose the FFT averaging on, and you can see that due to the integer number of frequency selection, it's there. Now how what happens with something like this, and you can see the side lobes coming up now. This is because I just chose the averaging option on, so that if we have an immediate increase of side lobe, many people do not realize that this is the energy appearing in the frequency bins, which are not the part of our main signal. This was what we saw earlier. Now let us see the effect of different windows. Because rectangular window is not a really good window. You can see a very high side lobe level. because these are relative gains. Remember, this QT GUI frequency sync always shows relative gain. So there is nothing in the absolute value, it's only in the difference. So it's maybe minus 10 dB here, and the side lobe is minus 6. So just minus 40, 50 dB difference between them. If you choose the Hamming window, you can see the side lobe level going down. Windowing is a subject which we did not discuss. I will recommend you to read the excellent paper by Fred Harris on windowing. It was published in 1978. How about Blackman Harris window? And you can see that the side lobes are going even further down. One thing you might have noticed is that this decrease in side lobes comes at a cost of increased a wider main lobe. So for example, if I go back to rectangular, closely observe the width of the main lobe. So the main lobe width is decreased.